At the end of the last video, I mentioned these things called matrix equations, and how they basically are going to allow us to solve these questions regarding span and linear independence and such very quickly. And so this video is going to kind of introduce that concept to you all. And more importantly, it's going to show the relationship between a system of equations, the vector equations you learned about last video, and the matrix equations that you're going to learn in this video. For starters, though, I need to introduce one concept that I'm not actually going to dive in super deep because we cover it a little bit later in the course, but the textbook kind of just introduces it and hand waves it and says, hey, you can just do this. And then you kind of just use the rule to work with matrix equations. And so I'm going to also do something kind of similar. I'm going to do a little bit more in depth than the textbook does. But at the very start, what I'd like to do is define matrix multiplication. So matrix multiplication. Okay. So, what does it mean to multiply matrices? That in and of itself is a massive can of worms. But for right now, I'm just going to say, if I have two vectors or two matrices, right? A matrix is a box of numbers. A vector is a very particular type of a matrix. Let's say I have two matrices, given, the matrix, we'll say the M by N matrix A, and we'll say P by Q matrix B. Then matrix multiplication A times B is defined. P.S. That's not a dot product. That's just me putting multiplication. A times B is defined only if N is equal to P. And the resulting matrix, we'll call it... resulting matrix, we'll say C, has dimensions M times Q, or M cross Q. So what does this mean? I think the easiest way to do this is through some examples. So if I asked you, can I multiply this matrix, so 1, 2, 3, 4, 5, 6, and this matrix is a 2-row times 3-column matrix with, say, another matrix, and let's make this one a vector. Let's just make this like 7, 8, 9. Can I multiply these together? Well, this is a 3 by 1, and I claim that because these inside values match, then you can, and the resulting vector or matrix, the resulting matrix that we're going to get out, is going to be a 2 by 1 matrix, and that comes from the 2 here and the 1 here. So, for instance, if I erased that and I asked you, can this new matrix that I've created multiply with the vector that I have there on the right? The answer is no. This doesn't work. It's not defined, and there is no solution for something like this. So the more interesting question is, how do we actually do this? And matrix multiplication can get there's like different steps to it. So I'm going to give us just the simplest version, which is specifically for something that is like this, and I'm just going to do it via example. So let's say I give you a matrix that looks like this, with like a V1 in here, a V2 in here, and a V3 in here. And let's say I give you another one that looks like X1 and X2 and X3. Okay, and this is a 1 by 3, and this is a 3 by 1. So the result should just be one entry, essentially. And I'm going to define this, define the multiplication using the dot product. Okay, so using the dot product. And what I mean is that this will only work out if we have a 1 by 3 and a 3 by 1. And the way that it's going to work, I'm just going to define this. This is going to be, you could write it v1 x1 or x1 v1. I'm just going to write it x1 v1 plus x2 v2 plus x3 v3. Okay, so I'm doing a little bit of hand waving here and not really justifying it, but I'm going to take this component and this component, multiply them together. That's how I get x1 v1. Then I'm going to add what I get when I take this second one and that second one, and I'm going to do the same thing for the last entry in both of them. And this, you're like, how is that a one by one? It is. It's one single term. If you want, you could put brackets here, but that is just one single entry in this matrix. This is a one by one matrix. It doesn't look like it, but it is. So the way that matrix multiplication works is, this row times column approach for multiplying matrices. Now, the reason I have to introduce this is because hopefully what I just wrote down there in pink right here should look somewhat, we'll say, familiar to you all. So let me write down a vector equation that we may have gotten out of last video. So let's see. So for example, I'm going to show the relationship between a system of equations vector equation, and this thing I haven't defined yet, and a matrix equation. And I'm going to do it using the vectors from the last video. So using v1 is equal to 1, -2, -5. v2 is equal to, let's say, 2, 5, 6. I think that's what it was. And then our vector b is equal to 7, 4, -3, like so. And similar question, so inspired by, in case we forgot, inspired by, is the vector b in the span of the vectors v1 and v2. Okay, so that's kind of where the premise is. So remember, we're going to start actually with the vector equation. So with the vector equation that we came up with this thing, or for this thing, was that if this is the case, there exists some, x1 times our v1 plus some x2 times our v2, and that equals our vector b, right? If this has a solution, then b is in the span of v1 and v2. Okay, and then we wrote this, we expanded this vector equation a little bit. We kind of wrote it out using the vectors themselves. 1, -2, -5, plus, for the vector v2, we had 2, 5, 6, and then 7, 4, -3. And we basically got to the point where we combined these, and eventually we got a system of equations. And the system of equations that we got was x1 plus 2x2. Here, I'll stick with my color theme. So x1 plus 2x2 is equal to 7. We had a -2x1, and then plus a 5x2, and that's equal to 4. And then last but not least, we have a -5x1 plus plus a 6x2, which was equal to -3. We got here. And we created a system of equations that was inspired by or came from this vector equation right here. So I'm going to put a box around our vector equation. I'm going to put another box around our system of equations. And then the very last thing we did here was we took all of this and we were able to eventually write it in such a way where we realized that this was the same thing as writing the augmented matrix 1, 2, 7, -2, 5, 4, because solving a system of equations, we did that in the first week of class, that this is the same thing we got here. And it turns out that this, right, there's one thing missing here, and it's the thing that I haven't described here, which is a matrix equation. So I'm going to go ahead, now that I've shown kind of the relationship between a vector equation and a system of equations, I'm going to explain what a matrix equation is, and I'm going to do it using the example that we have. So, what is a matrix equation? What is a matrix equation? And instead of me kind of logicking through this, I'm going to write something down and see if we can agree as to what it is. So I'm going to say, via example, and then I'll write a general definition here. So via example, let's let the matrix A, let's let this be equal to a matrix whose entries consist of the column vector v1 and the column vector v2. So that v1 and v2, just to zoom out, those are coming from the earlier part of our problem right here. Okay. So what does A actually look like, right? A is actually going to be this 3x2 matrix that consists of 1, -2, -5, and 2, 5, 6. Okay, this is a 3x2 matrix. That's what A is. And so hopefully using the little bit of matrix multiplication that I introduced earlier, so then we're going to let this new vector x just consist of our x1 and our x2. And again, I'm going to stick to my colors. My x is going to consist of my x1 and my x2 coefficients from earlier. Okay, so then let that happen. So the question is, what does ax give us? A times x give us. What do you mean, what is a times x? Well, a times x, I mean it in the case of vector multiplication here. So put a line here, I'm going to drag us up to the top. Well, a times x, that's going to be, that's the matrix A, which is v1 and has v2 as the entries. And then that's going to be multiplied by the matrix, or if you want to refer to it as a vector, the vector x consisting of those. And what is that supposed to be? Well, if we do the multiplication that we did before, it's going to be this first term times this term. And by the way, we should check that we can do this. This is a 1x2 matrix. This is a 2x1. So again, since the insides match, we can do this multiplication. So when we do this, if we multiply the x1 times the v1, we're going to get x1 times the vector v1 plus x2 times the vector v2. And we're going to make sure that these are actually the color they're supposed to be. x1 times x2. All right, cool. So we have those. And this is exactly the left half of our vector equation right here, right? That's the left half of our vector equation, which eventually led to a system of equations. All right, hooray, right? Maybe we're not seeing the big picture yet. That's okay. The whole point is that it turns out a shorthand way of writing this is a times x for the left side. A times this vector x, where a consists of the vectors v1 and v2, and x is a vector that consists of the thing that we're trying to solve for. Now what goes on the right-hand side? What's supposed to be over here? Well, this is supposed to be my vector b, right? That's supposed to be on the right-hand side. So just to make sure that we're not getting too lost or too far off track, what we just came up with right here, this right here, this is a matrix equation. That right there is a matrix equation. And more generally, let's give maybe a definition. So definition. Okay, so definition. A matrix equation is, guess what? An equation consisting of, you guessed it, of matrices in the form AX equals B. And I'm just going to leave this right here just for a sec. That just generically is what a matrix equation is. That's how it's written and how it looks like. Okay, so how does this relate to everything we did? Let's zoom back. Let's go back to the original question. Okay, so show the relationship between a system of equations, a vector equation, and a matrix equation using those. So at the start, we had a vector equation. We said, oh, this is an easy place to start right here. That's a vector equation. We also saw that if I had given you this system of equations to start with, which I didn't, I gave you vectors to start with, but if I had given you this system of equations to start with instead, that both of these, the vector equation and the system of equations, end up at looking like this matrix right here. That's what they end up looking like. It turns out that similarly, right, if A consists of those vectors, so this right here, if I write it as the little matrix 1, -2, -5, and then 2, 5, 6, times my little x1, x2, I keep saying I'm going to do the colors and I just get off track, x1, x2, equals my vector b, 7, 4, -3. It turns out that this, which is my matrix A, this is my solution vector x, and that's my vector b. This is the same way as writing the vector equation. It's the same thing as writing the system of equations, but it turns out with matrices, this is going to be very nice for us going forward. One thing that I want to point out is something that I slipped in with really quickly with, which was this x right here, this vector x, this is our solution vector. Now, what do I mean by that? That vector consists of our x1 and x2. Those are the things that we're trying to solve for in the system of equations. They're the things that we're trying to solve for in the vector equation right here. Okay? And so making the connection between all of these things, all three of these things, as I've written them, the vector equation, the system of equations, and the matrix equation, all have the same property, which is that they all end up in this matrix form. This is probably the most important part of this video. The idea that no matter how I write it, or how we think about it, are we thinking about it as the intersection of a bunch of lines? Are we thinking about it as, is B a linear combination of these vectors v1 and v2? Or are we thinking about it as A is a matrix that consists of those v1, v2 vectors, and we're writing it in this form, which is essentially saying the same thing, is B a combination of the vectors that live inside of A? And actually that's so important. I'm going to write it down over here. So having AX equals B is the same thing as asking, is B a linear combination of the vectors or of the, not just any vector, of the column vectors of A. Right? Is this true? Question mark. Okay. So that's what like a matrix equation is. Now, why is that interesting to us? Well, maybe it's about time that I just kind of crank out an example really quick. So let's see. So let's examine the matrix equation AX equals B, where let's just make one up, where A is going to equal, let's just make up 1, 2, 3, 4, 5, 6, and B is equal to 7, 8, 9. You know, what information can we get from this? What information can we get? Okay, so based on everything that we did before, this matrix A consists of a column vector, v1, and it consists of a column vector, v2. And if I write it in the form AX equals B, first and foremost, let's try and set it up in this form. So if I try and set this up, I'm going to have my matrix A, which is 1, 2, 3, 4, 5, 6. Now, my matrix X, my vector X, I'm going to leave blank for a second because there's a more interesting question to ask there. But then this is supposed to equal 7, 8, 9. Okay, so if that's supposed to equal 7, 8, 9, this first matrix is a 3-row by 2-column matrix. The B matrix, or the B vector, is a 3 by 1 vector. And I know that this, this is some m by n vector. But in order for this to make sense, these two inside pieces have to match, which means that my m is actually going to be a 2. And this also means that my n has to be a what? Well, we get that information because this 3 has to match up here and the n has to match up with the 1, therefore giving us that the n over there has to be a 1. So this missing vector that I don't have anything for, x1, x2, right? This is my vector x. That's like my little solution vector. If I wanted to know, right, it says, what information can we get? Well, you can ask the question, is B in the span of the vectors 1, 2, 3, and the vector 4, 5, 6? That is a question I can ask. Is that the case? If I want to solve this, you can just set it up immediately inside an augmented matrix. You can immediately just make a jump, 1, 2, 3, 4, 5, 6, and put 7, 8, 9 over here. And let's pretend that we solve this thing, right? Let's just say that we pretend that we solve this, and we get here. We get 1, 0, 0, 0, 1, 0, and then for the right part, we're going to get, 3, 4, and 0. So I claim that writing it in this form implies that x1 is equal to 3 and x2 is equal to 4. This should make sense. You're like, why does this make sense? Because if in your head you relate this back to a system of equations, this was solving the equation x1 plus 4x2 is equal to 7, 2x1 plus 5x2 is equal to 8, and 3x1 plus 6x2 is equal to 9. That matrix corresponded to this, and this setup came from solving x1, the vector equation x1 times our times our v1 vector 1, 2, 3 plus x2 times our v2 vector 4, 5, 6, and asking does that equal 7, 8, 9? So all of these forms are all the same. But the difference is that now if I set it up in this particular way, I can just jump straight into an augmented matrix and solve it and figure out what this missing x is right here. And that's going to be like a very common theme moving forward, which is we're going to really like writing things as matrix equations where we're very interested in solving that for that little vector x, which we call our solution vector. So one last thing just to really kind of drive something home. If I give you just this box of numbers, okay, a random box of numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I ask you, what does this box of numbers represent? At this point, hopefully we have enough procedural fluency and conceptual understanding to say that, well, this could be a whole bunch of stuff, right? What could this box of numbers be? This could be, just a 3 by 3 matrix. Could be nothing. This could be an augmented 3 by 3 matrix, right? In which case, the last column here, right? In which case, the last column, those are numbers, and then the first two columns correspond to our x1s and our x2s. So, our first two columns correspond to variables. All right, great. What else? Well, if this is an augmented matrix, then it answers the question, it's asking the question, does AX equal B have a solution, right? Have a solution. Right, that's a question that it could be asking, where this is my vector B. This all belongs inside my 3 by 2 matrix A. And if I can solve this system of equations for some x1 and x2 that live inside here, x1 and x2, then that would answer that question. So does that have a solution? Asking that question also inherently asks, is B in the span of, we can say the columns of A, right? Is that a case, right, where this is a column vector V1 and this is a column vector V2? We could say, is that the case? There's a whole bunch of different ways of looking at this. We could also go back to just the OG way of looking at this, where this could be a system of equations, which kind of, reflects the augmented case, where this is just x1 plus 4x2 is equal to 7, 2x1 plus 5x2 is equal to 8, and then 3x1 plus 6x2 is equal to 9. So this box of numbers is now kind of developing a meaning, and we're not just stuck on what we learned in Algebra 2 class, which is, oh yeah, this is like, we're looking at the intersection of some lines. We can view this in completely different ways and talk about vectors, and eventually we're going to learn our vector spaces and span and linear combinations and linear independence, and right, because asking, if it's in the span, then that means B is linearly dependent on V1 and V2. But if it's not in the span, then B is linearly independent from V1 and V2. We could keep going and going and going, and we are going to build off of this in the next video, where we go into a little bit more theory. So I think this is a good place to stop. There's a lot of information in this video, so I do encourage you to go back and watch certain parts of it again, and then when you are ready to move on, head on to the next one.